Hello, everyone. I hope you can hear me okay. If you can give me some indication in the chat that the sound is okay, I'll not be too worried and fiddle. Yeah, awesome. How many people have we got so far? We've got 25. So class is a fair bit bigger than that, so hopefully they'll turn up. I hope everyone's doing okay. This has been a bit of a disaster again, but what can you do? Yeah, I hope you're all doing well. It's a really trying time. I feel sorry for younger people and students having to go through all this stuff. It's hard enough normally having to do all this stuff. Big kerfuffle. So well done. It's one of these times I appreciate being a software engineer because it's really easy to work remotely. If you set up your organization correctly, it's pretty normal. You're sitting at a computer, as long as you've got internet, you can make it work. Cool. So I guess we'll get started. I had a question at I think it was the end of last lecture. Someone was asking me about beginner resources for Julia. I thought really hard about it. There's a few, like, you guys can look on the internet better than I can. There's a few things on Google. You can have Julia Computing have a few video series. So if you go look at Julia Computing's YouTube page, there's some stuff there. I was thinking about it though. The thing I would recommend almost instantly is if you get in the habit of doing simple stuff using Julia. So I remember doing this for years with Python. It's like, if you have a little simple calculation you need to do, instead of going for a calculator or Excel, just go into an IPython session, do this. So same, go into a Julia session and just start doing simple everyday things. Use that and start plotting things. And if you have something you do repeatedly, like a budget or something, you can code that up. It sounds a bit silly, but it actually, for familiarity and getting used to doing simple things, I think that's like the best thing you could be doing. I hope that's not useless advice, but we'll just give it a go. Okay. Yeah, so I will share my screen. Okay, we'll go back over to, okay, election notes. So just in terms of where we're supposed to be and going, I think it's pretty good to look at the schedule. So we're into week 2. We're supposed to finish up this section 1 and start on section 2. Section 2 will be a little bit of a monster, so that'll finish in week 4. Then we'll go into section 3. So hopefully today we'll get through section 1 in this lecture, and then we can move on to starting on section 2. Any questions so far? How's everyone going with how are you finding your first week back? All good. Okay. First one to answer answers for everyone. So we'll get going. So last week, I went through the square root. So I hope all of you watched that video because I thought it was really interesting. They did a good job of presenting it. So we went through square root, this inverse square root, basically trying to give you a picture of how to do these simple everyday things when you're in a programming language. So things you're interested in as a mathematician, these functions. I'm going to give you a second case, which is the factorial. So we'll go through how you do factorial on a computer. This one will introduce just like the concept of factorial. You should all know that. It's a good opportunity to introduce recursion. So recursion can be a thing that people have problems with when they're starting to learn programming. It's kind of can seem a bit weird that you can do this and that it's a way to do it. It's just one of these things. It's a bit of a mind flip when you get used to it. You just start doing it all the time. We're going to introduce a new type. So last time we were talking about integers, and we talked about signed and unsigned integers and their bit representation. We're going to introduce something called a big int. Talk about some extensions to analytic extensions. So we'll say like gamma function, and we'll talk a bit about approximating. So factorial is this combinatorial function. You come up all the time in probability because you're counting ways to do things. So factorial is, if you're not familiar, it's just the product from 1 to n. So it's given this little exclamation symbol. In Julia syntax, exclamation symbol is used for function. If you have that on a function, it has a special meaning. I'll talk a bit about that hopefully today. So few basic ways. So factorial, I had to make sure I closed my Julia session. So factorial is built into Julia because it's really useful. So factorial 10, done. This is another one, the syntax, that this is mostly just to introduce syntax. So although you're used to doing multiplication like 1 times 2, I hope you can see my Julia session, everybody. Is that fine? Yep, cool. Okay, so 1 times 2. Like everything in Julia, it's a function. So it's actually a function that takes 2 arguments. And this is just special syntax to make it look more like maths. You can actually call times like you would any other function. A little bit weird. You know, you're more used to 1 times 4, but it's a function. So this is just syntactic sugar, they call it. So a little bit of syntax that makes it happier for users. So it's actually a function and it takes 2 arguments. This just gets converted into that. So got this slightly weird one here where we can say, so you should be all familiar with 1 to 10. We'll make an iterator from 1 to 10. So this little bit of syntax here, what we're doing is these 3 dots are called splatting. So what it will do is it will take all those elements of that iterator, put it through this function. So this is a little bit of weird syntax to do that. It's very useful sometimes when you have an iterator or a collection. You can splat it out and pass it through the operator. So you multiply that. This one's another way to do it. So accumulate is another function you might want to use sometimes. So that basically applies this operation 1 at a time. So 1 times 2, blah, blah, blah. So last just takes the last element of that collection. Easy. So this one is probably the way you'd probably think to do it if you're just thinking of loops. You just do that. Big point here is this global is declaring a global variable. You really be careful doing this. The reason you do this is because of scoping. So where variables are defined. So when you're doing it in a REPL session, if you don't wrap this in a function, you need to say f of d is a global variable so that it exists in the loop. If you don't have global there, it won't know what f of d is. It won't update f of d. Oh no, it did, because I've already declared the global. If I started a session, got rid of it, because I've already declared there's a global, it's already happy. So that's kind of annoying. Usually, good practice in Julia is to make a function. So foo of m, you'd go d equals 1, or I equals 1 to n, d times equals I, and d turns d, and then you can go through again, and you get the same thing. So again, if you're not familiar, times equals in that one is take the value, multiply it by this new one, make the new thing equal to that. You could do something like x equals x times 10, you know, but you can also do x times equals 10. Just a nice another bit of syntax. I don't know if that's new to you, but you're gonna, starting a new language, you get this brain dump of all the new things you haven't seen before. So they're just different ways to do a factorial. So We've got some built-in method. We've got this sort of by hand method. Okay, good question from Victoria. So what are the rules for indents and Julia functions? There are none. I'm being lazy in the REPL and not putting them in. It's more just for, it looks nice. It's not like Python where the indents define control flow. That was actually a design decision by the Python creator to make it always have nice syntax. So you can't be lazy. You have to make it indented to make it do the right thing. Julia is not like that. It's not that prescriptive. As long as you have it wrapped in the for, you don't need to do the indents, but you should do the indents. I'm just being lazy because I'm trying to type quickly. When you get into an editor, I don't know, we haven't quite got up to talking about, you know, development environments yet. If you have a nice, you start using VS Code, it'll give you some hints that your indents are off. So you get these little nice little lines to make sure you're doing the right thing. So no rules. You can do whatever you want, like I just did. Makes it look ugly as hell. You should be a good person and go tab, much less horrible to look at, but you don't have to do it. Hope that's clear. It will do exactly the same thing. Okay, it's just a bunch of different ways, different ways of doing the same thing. So this thing in computers, when you're programming, you can do the same thing 100 different ways. Clarity is good if you go for simplicity and clarity. So that will give you the same answer, which is what you'd hope for. We're all doing the same thing. So factorial. So mathematically, if we're going to define it, we can define it, and you guys should all be happy with this, is we can define it with a recursive definition. So we can say, as long as you're bigger than 0, you can say that n factorial is n times the factorial of the one beneath it. That's fine. That's the thing. That's how you define it, rather than going product of n for over the things. You can just define this thing recursively. Now, this is actually a completely fine thing to do in a programming language. Defining functions recursively is a good thing sometimes. For some problems, it makes your problem much easier to define it this way. Can have some problems about reasoning about what's going to happen, like how many times this recursive call is going to happen, and you know, maybe you'll end up using too much memory for certain types of problems. So you know, a little bit careful with how you set it up, but this is actually completely fine. So we're calling this function within itself. That's the recursive definition. So this maps 1 to 1 with this guy. If n equals 0, we return 1, else we return. So we've got multiple return statements here. N times my factorial n. So this guy, when it hits this thing, calls itself 1 lower. It calls itself 1 lower, it calls itself 1 lower, depending on what you initially set n to. So again, this is another way to set this guy up, just to show we're not lying. You get the same answer we had before for all of these ones. So recursive function definition, super useful. Now, with a bit of logging, so this guy above, I won't bother running this because it's kind of boring to see it twice, but this is a way, we're putting some print debugging. So it's always a useful tool when you're programming to just see what the hell's going on when you run a function. If we're going to see what it's actually doing, so it's calling this function at the start. So we're putting a little print statement and calling it. So this syntax here with this $ means put this value in the string. So if I said x equals 2, println hello x, it just puts the 2 in there. So if you want to put an int into a string, you can just do that little syntax. That's what's going on there. So it's taking the current value for n, and it's going to go, I'm calling my factorial with this, and it'll do stuff. And then when it gets to the end, we've got this return value. So it's returning from the call of my factorial with blah. If you run that, I'll let you do it yourselves. Hopefully you're all set up with Julia and going now. A lot of you have had problems. It always sucks setting up a new environment. if we call this thing, it's going to go, I'm calling it with 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And then when it hits 0, it actually gets the value. And then it comes back out and multiplies it by n. So then it goes 0 will give you 1 times the return from 1, blip, 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 and then give you the answer on the way out. Yeah, so if for some problems, and we'll come up for this, we're going to talk about sorting in Unit 2. Some problems are really, really natural to set up as a recursive function call. So it can make your problem really easy. You can divide it up into subproblems and then just keep calling the same thing. Sometimes it's really unnatural. You know, it's easier just sometimes to go back up to here and just do a loop. But sometimes particular problems having recursive function calls make it easy. More or less difficult things. You can stack trace is another thing you can use. Okay, is that clear? Can be a little bit of a switch to think about these things, but it's fine to call it. So Julia has a lot of very flexible syntax. So that function we defined long-windedly up here. So 1, 2, 3, 4, 5, 5-line thing. We can turn this into a one-liner. Again, we're going to go. So you can define one-line functions in Julia. That's fine. My computer's locked up. Can everyone hear me still? Hello?
I can still hear you.
You can still hear me?
Yep.
I'm frozen for some reason. Sorry, guys. What can you see my screen? Is it my screen moving or is nothing happening?
The mouse is moving, but not much else is happening.
No. Sorry, I'm not sure what's happening, guys. This is a pain. Sorry, I might have to leave and rejoin. Hopefully this doesn't stop the session, guys. I'm really sorry about this. I'm not sure what's going on. I'll get back to you in 1 second. I'm very sorry. Hey everyone, I'm very sorry. I'm glad it stayed open. That was a bit of a disaster. Okay, sorry, back to it. We're all good. Sorry, yeah. That threw me. I'll just make sure the chat's. Oh no, Victoria's ended up as the host. Sorry. Okay. Okay. Running too much stuff for work. Okay. Sorry, we're back to this one. I don't think you should have to leave and rejoin. Oh, let's just see if you've got ultimate power, like you said. That's fine. Yeah, something like that. Okay, sorry, back to it. Okay, awesome, that works. Who knows how that works? The mysteries of Zoom. Okay, so back to it. I'm very sorry. So we got my factorial here. So this is the same thing as above, just a very compact thing that does the same thing. More syntax here. We have this funny expression with a question mark. This guy's called a ternary. A ternary expression. So just for spelling, what this means is you have a conditional. So what we can say is like x equals false. And we go x question mark. It's like this if else logic. So you can make it really short. So if x is false, I'm going to return 0. Otherwise, I'm going to return 1. So if I set x equals true, get 0. So this if-else logic, you can squish this down into something quite nice sometimes with a ternary. So we can do a one-line, you can do a function in line, and we have this ternary expression. So if n equals 0, it's 1, otherwise call my factorial. So exactly the same thing above as above. And interestingly enough, we can look at code lowered. I don't think we talked about code lowered. Last time we talked about code native and code LLVM. So this is a in-between step just before that. So you go lowered code, LLVM, native code. You can do a macro to look at what Julia turns this into to give to LLVM. And so I'll just have a go at this guy. And we can see if we look at, I'm just doing it in the REPL because we'll get a bit of, oh no, it's not much better. There's no code highlighting. Anyway, Julia is clever enough to work out that these two things do exactly the same thing. So there's actually no difference in how Julia executes this thing and in low-level hardware stuff. So if you time all this stuff, you get exactly the same thing. So the lowered code representation for these two different functions, this one-line one and this multi-line one where you're just doing if-else statement. Sometimes you can switch it out for a ternary and make it a bit nicer, depending on how familiar you are with doing ternary expressions. Okay, so now, a bit more interesting, hopefully, is we can start to have a look at how big a factorial we can compute. So ints and 32-bit ints, they're big numbers. Like the biggest number you can represent in 32 bits and the biggest number you can represent in 64 bits are quite big numbers, but factorial is a function that grows very, very, very quickly. So you're going to run out really quickly, unless anyone's read the notes. But if you have a guess, like how big a number do you think before you're going to start to have problems, do you think, for factorial for ints? We'll just take a quick vote in the chat. You've read it? Okay. Yeah. So yeah, it grows really quickly. So the way we're going to do it is we're going to use a thing called Stirling's approximation. Have you come across Stirling's approximation before? It's one of these things that it was very, very useful in, say, probability, statistical mechanics. If you're doing physics, you'll come across Stirling's approximation to do analytic representations of factorial. So this thing of like, if you have a probability distribution and where you're counting something and you're trying to normalize it over all the possible ways something could happen, this factorial pops up all the time. So if you're doing permutations or combinations, you get factorial popping up. And so like, you know, it's impossible to calculate that. Multiply, 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 it gets too big too quick. So there's this useful, so a way of dealing with it analytically is to do Stirling's approximation. There's a bit of stuff here that you can go through yourself to show that Stirling's approximation is reasonable. The first one is that n factorial is less than n to the n. That approximation gets worse as you go bigger. And basically you can think of these things as correction terms to make the approximation more correct, approximation better. So hopefully here, so just printing out the ratio between factorial n and Stirling's approximation n as we get bigger and bigger. So it gets better the higher it gets. It's pretty poor, you know, 8% off at 1 and getting down to, you know, less than 1% as you get up to 10. So what we're going to do in these notes is to look at Stirling's approximation to see how big an n will be able to go for a Uint64. Now again, remember I was talking about previously that these guys have shenanigans where they can do funny things. So if I actually do this, it's going to do something quite weird. It's going to go to -1. Even still, if I do 2 to the 63, it's going like negative. So again, this is to do with this finite bit size representation of integers. So you can't just, you've got to be careful. Just naively typing this in, 2 to the 64 will give you a silly answer. It will give you 0. So if you just type a number in Julia, this thing goes immediately to an int64, which isn't what we want. We want to see how big we can go with uints. So you can get away with this guy, but you'll get this hex string that's not quite what you want. But if we print it, we can actually see what this number is. That's a big number, so I can't even count how many zeros there are there quickly. Now, with floating point though, however, so I've hinted at floating point, and floating point is something like scientific notation for representation as bits. So you've got a mantissa, which is the bit out the front, an exponent, which is the power you're multiplying. So a times 10 to the power of something as bits is what floating point representation is. So this, however, is absolutely fine. You can do that. Floating point, you can go much bigger than you can with the ints. So really useful function is type max. Type max, you've also got so type max of int64, type max of uint64, and type max of float64. Now, that's 63. That's infinity. So you actually have these special values in floating point numbers for not a number, infinity, minus infinity, as well as all these numbers in between. Another one you can also do type min as well. Type min minus int. Type min for this guy, for the signed integers, will be a negative number. Type min for uint64 is 0 because they're signed integers, they're unsigned. So the smallest number you get is 0. So we can do more with uint64s than we can with int64s. So there's a little bit of code here to sneak through and go like, okay, again, declaring a global because it's not wrapped in a function, we're just doing it in the command line. So when will you reach the limit of type max of int64s? So going through, so doing the function for Stirling's approximation, we're going to call that and go, when does that stop being less than the limit? It's going to break out of the loop. So it's going to be at 20. So someone in the notes got it right. So that's for signed ints. So you could look at the same for uint64. And you can verify this by just putting factorial 21 and it will explode. So that won't work. It's too big. And this overflow error. So useful error for Julia. And it's actually super useful in Julia. this time. It's not always the way. Sometimes you'll get functions exploding and you have no idea what's going on, but this actually tells you how to fix it. It gives you this hint of going, call factorial big 21 instead. So the type of big 21 is a big int. So big is a function, again, ever confused, question mark, big. And big will give you the equivalent representation with arbitrary precision. So you give it a type. So I'll take the type of the number. So this is type annotation. So I can call big with a float and it will give me a big float, but for now we're putting an integer in, so it will give us a big integer. So what this means is that we can use the normal operations like plus and multiply for these arbitrary precisions. So it doesn't care about the 64-bit limit anymore. It will go to very, very big numbers. So in fact, as like here, factorial big 21, you can also just go big int 21. Ants, if you want the answer to the last thing you evaluated in Julia. I don't know if you guys have learned that one yet, but you can make a big int directly from, but if you try and make a big int 21.0, oh, that actually worked. That's really surprising. Anyway, I didn't think that would work. But if you go big 21.0, because this is a float 64, this thing will be something else. This will be a big float. Okay, so we don't have the same problems anymore. So now we can go, to the limits of your memory now. So we can go into the 10 to the power of 3 and take factorial of that. So we didn't print this out because it's big, and we just counted up how many digits it has. So it has 2,568 digits. So that is a very, very, very big number. Yeah, so this is a useful type, and it will come back to you guys when you get up to Paul Verbeek's section. You will start doing some stuff with big ints. So this will come back. It's very, very useful if you're doing stuff with, oh, whoopsie, there's a factorial. So I'll say this guy for you guys. If you see some spelling mistakes through here, we have this course as a GitHub repo. So you should be able to make a pull request. So we'll teach you in section 2, I'll start teaching you a little bit about GitHub. So you can actually contribute to the course by fixing stuff up, which would be great. Thank you for that, though, Natalie. Yeah, so hopefully this is like a live thing, so you guys can learn a bit about how to use version control stuff, and we can make it better as we go. So again, in maths, you'll be interested in extensions to things beyond where they, so factorial isn't defined on the reals. So good thing is Julia will explode if you go try and call this with floats with try and call factorial on a float 64. So it's given this thing, you'll see this a lot in Julia, method error. It means you're calling a function with the wrong type. So back here, I know it was in my, when we looked up big, T is of a certain type. So when you're defining a function, you can go, sorry, this is a little sideways. I can say X is an int and return X plus 2. And so if I go high 2, it will do something. If I go high with 2.0, it will do the same thing where it goes method error. So I've defined X will only work if it's a type of type int. This is useful for catching things like this. So it's not in Julia, it's not a hint for the Julia compiler about how to deal with this stuff. It's more about catching certain types of inputs, and maybe you want different types of the same function to run on different types. So this type annotation is mostly for that. So in base Julia, there is no factorial for the reals, but mathematically, this is something that people have been interested in. So this thing is called a gamma function, is the extension of factorial to the real. So this is defined in terms of an integral from 0 to infinity, x to the z minus 1, e to the minus x dx. So now, this one will confuse you if you're following through these notes. using special functions. So special functions is a Julia package. If you don't have it, I hope you all have seen this by now. You square brackets, add special functions. I already have it, so there's nothing to do. It'll go through. So this is not part of base Julia. It's a repository that somebody else has made that has some useful stuff in it. Get out of the package manager, Control C. So now I can sort of shortcut and go Factorial 6.5 will actually work because in special functions, if I go at which, so this will tell me which version of this I'm using. So it's using factorial x number in special functions, and it gives you the path to the code if you want to have a look at this thing. So you can open this file and have a look at what it's doing. So it will call a gamma function. So shortcut to the end. Okay. So we're going to go, there's this thing of a gamma function here. So hopefully my notes stayed up. But this is basically, Yoni's just written a version of this. So we've got the integrand, the part inside the integral, and we're going to do a crude approximation to the Riemann sum. So you should all be familiar with this, hope, from first year calculus or high school calculus, is that you can define an integral. One way you can define an integral is by doing a bunch of boxes. So we're going to evaluate the thing here, and we're going to go, there's this little box, this little box, this little box, this little box, approximates this integral. And the idea is as the limit as the x goes to 0, so you make more and more boxes, the sum of these boxes will approximately add up to the integral. So it depends on this spacing. So Riemann did, the proofs of this in the 19th century, that this is a fine thing to do. Maybe you guys have hit Lebesgue integration if you've got singular functions, things like that. I don't know if that's a thing you guys have done yet. Alternative definition for an integral. But this one's actually useful numerically because this gives us a way to generate an algorithm for evaluating integrals. So all you do is you just evaluate this thing you have on a regular grid, and we just get the little boxes and we take the area. So the area is just base times height, sum those all together. That's a reasonable approximation to the integral. I don't know how many, if you've done numerical methods courses yet. We'll see a little bit of that here. So that's all this function's doing. It's just doing what I drew really crappily here. It'll just go, okay, I'm going to evaluate this thing, multiply it by the box size. So the height is the value of the function, blah, blah, blah. And that will give you something like the gamma function. So gamma 6.5 gives you this. This one gives you, where does it start changing? That's actually pretty good. So down here is where the digits start to change. Just a bit off piece, it's like, do any of you know what would be a better way to calculate this integral? Just as a off the cuff question, what can you think of to improve this method of integration? Trapezoids? Yeah. So that trapezoid method is, instead of doing a box, we can just draw a little trapezoid at each one of these. Trapezoid, trapezoid, trapezoid. So you're much more likely for a smooth curve like this one. Trapezoid methods a better job. You could also do polynomials. So you could do an interpolating polynomial. So there's all these higher order methods of integration that usually based on some smoothness criteria, you would get a better result for integration. So you can use bigger boxes and get a better answer. Question to think about in terms of computational complexity. If we were doing this integral in more dimensions than a univariate function. So if we had a 2-dimensional function, how does this grow with dimensions? If we're going to do this sort of box counting method. So how many boxes would you need to do a 2D function? This is n. Yeah, n squared. Good, 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 good. So this actually grows to the power of the dimension. So doing integration with these quadrature methods actually gets really, really hard as dimensions grow, because it'll actually grow like n to the n. Or n to the m, where m is your number of dimensions. So if you have a function that's in, like, say, 100 dimensions or 1,000 dimensions, these methods are inaccessible to you. That's actually part of my day job, is doing very, very high dimensional integrals, so on a computer. So just a hint about some interesting stuff you can do. So we were talking about factorial before. So any method that grows like a factorial is bad. You will be in trouble. And this thing comes up in optimization, in machine learning, in statistics. It's called recursive dimensionality in machine learning and statistics, that as you get to high dimensional spaces, integration becomes very, very difficult to do. Sideways, back to the notes. So if you look at the gamma function, this is one where you guys will be better than me, because you're better at being mechanical with calculus. You can do integration by parts, and you can show that this has a recursive definition that is just like factorial, which is why this thing is considered an extension to factorial over the reals. So this definition give you one, and you can just go. So we've got some little code, bit of code here that goes like, compare factorial versus gamma plus 1 for I equals 1 to 10. So you get the same answer, so all the way down. So for integer values, gamma function and factorial, no, gamma plus 1 equals factorial. So this is why you can consider gamma function, and that's exactly what special functions do, to extend gamma over the reals. Okay, so it's not defined at some points. The negative integers is not defined because of this extension. It goes singular at these points. So you're going to get this domain error. N must not, with -1, n must not be negative. So here's a plot where Yoni's gone through and he's cut out the parts where it will be undefined, so that we can actually make this plot. And you can see these singular points here. It's shooting off to minus and negative infinity. So the useful, in terms of Julia, this useful function, I'm sorry, blah, 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 blah. This one's a useful function for you guys to go. So set diff. So again, you're confused, going to Julia, question mark, set diff. What does set diff do? It constructs the elements of a set in S, but not in the iterables iters. So maintaining order. So if you've got 2 arrays, 1, 2, 3, 3, 4, 5, it will do the set diff. So 1 and 2 are in the first collection, but not in 3, 4, 5. So it will give you the difference between these two. So treating these guys as a set and extracting the differences. So that will take away, I should see. So it should cut out -3. If we look, let's see if I can actually get this in a simple way. Maybe not. Oh. Another useful one. So I'm going to try and find all the values where y equals -2, and there are none. But if I went to 2, that guy's in there. Yeah, that's right. So yeah, you can do intersect. So we'll talk about this later in section 2. We're going to talk about some data structures, but a set is a thing you can have in Julia. And you can do intersect, but you can do intersect with arrays as well. So you can do union, intersection, set diff. So you can do all these normal sort of low-level set operations. Yeah, so basically that's just a little bit of syntax. We've talked a bit about factorial, takeaway stories. So if I can summarize the bits I think are important that we just talked about. I think the number one thing to take away from this one is this recursive, apart from the syntax stuff's always good. It's good to know about ternaries. I've actually seen this as a software engineering interview question. Like, do you know what a ternary is? Because it filters out a lot of people who haven't done much programming. It's sort of like, if you've heard of FizzBuzz, that's like a programming test to see if you can code. Like, one of these simple things you should know about is a ternary. But the big one is recursive definitions are fine. You can have a function that's happy to call itself. And for some problems, when you're doing optimization, sometimes is one where this will come up. But also, we're going to talk a bit about sorting in the next section. So recursive definition of sorting algorithms is really, really useful. We're basically just going to do the same thing. So I take away that, this is a thing you can do. And for some problems, it's a really, really natural way to set up a problem. And it will make your life much easier. Ternary. I hope I can spell. You're asking me for spelling. Ternary, because it takes it's a 3-valued function, binary ternary. So you've got 0, you've got I think that's the etymology is because it's got 3 values. So you're going to go like true. So most of these low-level functions only take 2 arguments, 1, 0. So you've got the value it will return. The condition you evaluate, some predicate, what you return if it's true, what you do otherwise. Hope that's clear. So recursive definition. In terms of the factorial, I think learning about this new data type, the big int, is really useful. Big int will come back for you guys. And also, again, be careful of trying to do things like this when you're using ints and unsigned ints, when you're doing these 64-bit numbers or 32-bit numbers. This will bite you. I've had bugs, sorry, not that one in particular, but this one, where this guy wraps around underneath. That's why I was trying to hammer on about it in the first lecture, because this will be a bug that you will get if you're doing mathematical stuff. You'll get things that get too big really quickly. And you don't quite think ahead, and you get one of these overflow things where it will come back up underneath and get very, very strange results. Okay, do we have any questions on this little part of the section? Or is everyone happy? Okay, I guess we'll take a 10-minute break then. If you have a question, just hit me on the chat. I'll be sitting here having a cup of tea. So, oh yes, set diff. Oh, sorry, you don't get what it does. So we have 2 collections for set diff. Oh, sorry. Can you copy and paste in the Julia REPL from outside the REPL? Do you mean, can I copy that? Oh, God. Zoom crashed on me. This is really terrible. I'm very sorry, everybody. I've lost my chat history too. Sorry, if you can repeat the question, we can work through. And I will... This is teething problems. It's great, isn't it, everybody? Okay, so set diff, if you have two arrays, we've got an array 1, 2, 3, 4, and we have an array B, 4, 5, 6, 7. So if I go set diff A, B, so it will give me the elements of A that are not in B. So 1, 2, and 3 are in A, but they're not in B. 4 is shared by B and A. If I flip it around, give me the elements of B that are not in A. So it'll give me 5, 6, 7. There's 5, 6, 7 are in B, but not in A. Okay, sorry. The pracs this week be at one certain time or at individually scheduled times. I'm sorry, Ella, I don't actually know the answer to that. I don't know much about how that's. I think shoot Yoni an email would be the way to get an answer quickly. There's lots of stuff on Piazza. I think that's usually the way the go-to thing for in between, Ella. So if you have homework questions that can't be resolved in our pairs, we save the questions for the pracs. Feel free to shoot a question on Piazza. I think they let you wait a little bit before they let you work it out. I can give you broad hints, but I probably shouldn't do that. If you have any like conceptual questions rather than specific questions, I'm happy to take those. I should actually say to you guys, I got competitive with Andy, who's going to be taking you for the third part of the course. He works with me about question 3. So we managed to, I should say, Andy managed to get the Goldbach pairs in under a second. So if you want to benchmark the speed about how fast you can get it, it's possible to get it down to that fast. Wouldn't expect you guys to be able to get it that fast, but we just had a bit of a competition about how we could do it, how quickly we could get it done. So a question from Siana, I hope I'm pronouncing your name correctly. For the gold-back pairs, do we have to compute them all, then select 20,000 at random, or compute just 20,000? No. So number one, unfortunately. So you have to do them all and then select a subset. So the challenge is to get you to think about how you could reorganize this function to be efficient. In terms of a really broad hint about this sort of stuff is like, try and do things only once. Like there's no point doing the same thing twice. General approach to problem solving for performance is to just do things once if you can. Think about how you can rearrange this problem so that you're only doing things the fewest number of times possible. So before, when I was talking about integration, like, you know, things that scale as polynomials or blowing up to factorials are bad in general. So if you can think about how to flip something around or cut stuff out so that you're not continually doing the same thing, that's the way you get efficient. You can also do tricks like using the features of Julia to speed it up, but in terms of the algorithm you're doing itself, that's the trick to performance in general. Algorithms win. It's why you know, having clever people, mathematicians doing this sort of stuff is important, because thinking algorithmically is a really important thing. Hardware has gotten better and better over time, but the performance gain you can get from being clever with algorithms is usually more important. Okay, so I'll start again, guys. I hope you're all ready to go. Any other questions before I start? Or everyone happy? I will try not to have my computer crash on you randomly again. I don't know if I can control that, though. I'm going to be spending the night trying to work out what actually happened, if I can. No questions? I'll start then. Okay, so first two parts of the introduction, we've looked at functions. So there's more to computers than numbers, though. You know, you've also got to deal with text input and text values. And even you can think of a programming language itself. There's a bunch of text values. So putting these symbols in, they have a syntax that gives them meaning. Otherwise, they're just random things. So that's what we're going to look at. So dealing with strings, text, and natural language. So Julia has a big section on strings. You can read the documentation in Julia. I encourage you to read it if you're confused. And again, it's an open source project, so you can actually request or update the documentation yourself. You go to the Julia GitHub and raise an issue if you're confused by something in the documentation, or probably ask on, they have I've forgotten what it is. They have a chatty forum thing. I've forgotten where that one is. Ask questions there first, or search through, ask questions. And then you can, if you actually have a problem, think something's broken, or you think it could be improved, it's one of those things. It's like, the beauty of open source is that things actually get better over time. It's doing stuff like this in the open makes things get better. Yeah, there's a Slack. There's also, I think it's a discourse. I think there's like a Stack Overflow-y type thing that everyone uses. I'll send you I'll have a look through and get the links and send it to you. But afterwards, I'm just having a bit of a brain moment. Nothing's clear. Okay. Focus on different. So we're dealing with strings. So you've seen this already. So the way to input a string is, I was doing this with the print line. So hello, we've done that already. So again, if you want to know the size in memory, we've got this size of function. This should just be the number of characters, 1, 2, 3, 4, 5. So 5 bytes. So there's 8-bit representation of each of these characters in this array. These strings are an array. So we can use, so begin is another useful thing. So we can do begin to get the first element. We can also do 1, you know. It's useful if things don't necessarily start at 1, but from the beginning. You can do end as well, like if you don't know how long something is. Begin and end are really useful. So you can do S, okay, so you get a bit of a hint about what's going on in here. It'll give you what it is. So type of this thing. So we go, this is really useful for, you've got a variable, you want to know what it is. You can do type of S is a string, type of S begin is a char. So an array of characters is what it's doing. So there's some stuff in here. Again, if you want to do some stuff, that's begin and I don't know what to do. Hello, hello, hello. So 4 times, take it to the power of 4. So from begin to end -1. So this is going from, yeah, anyway, just silly syntax stuff. Not so interesting. So basic form of representing characters is Ascii. So have you all heard of Ascii and Ascii art? Ascii is the really old one, where 1 byte integers are translated into characters and vice versa. Printable characters start at 32, which is white space. So we've got a little bit of code here to print out an Ascii table. So it's giving it in decimal, hexadecimal. So hopefully you guys are all familiar with this. So we've got, this is hexadecimal starting at 20 up to 7e, and it's doing a tab. That's the /t. OX string blah. So tab character. So this is just to print out this table. It will give you the decimal value, the hex value, and the character. So you got white space character. And it's basically all the characters you'd be interested in for Latin alphabet, and the normal symbols you'd use is what's included in Ascii. So basically, you know, less than blah, blah, blah. You've got capital letters, lowercase letters, and some brackets and stuff. So that's Ascii. You'd notice in Julia, we've been doing, I'll just talk a little bit about it, you know, like you've got Unicode characters too in Julia, but that's a function. But you can represent more characters than Ascii. So generally there's this thing called the Unicode, which is an effort to try and standardize all the characters people use in all the languages of the world. And depending on how many you include is how many, you know, what size that thing is. That's a big effort, particularly for, say, Chinese characters, because, you know, there's lots of those, particularly like there's different, depending on the language, you know, there's standard versions and ancient versions of characters, and which ones you want to include in the set and which ones you don't. But Ascii is like this little subset you'll see all the time. Yeah, so Unicode is more for displaying all the broad sets of characters that you might be interested in. So this thing to notice is that if you want to make a char character, single quotes, so again, type of A is a char, type of this guy is a string. So if I try and say something like A equals, so is this equal to this? We'll go, no. But if I pick off the first element of A, it is the same thing. So a string is like an array of chars, is the way to think of it. So because this is a number though, strangely, because Unicode's got a representation, you can just add. So this is kind of useful. Unless you go too far, 34, you're going to get something weird. You're going to go into the Unicode characters. So -3 or 4, you're going to get a bracket, a bit of punctuation, which is not what you want. But you can just add to these things. If you go too far beyond the Ascii, you end up in Unicode, which is that thing I was saying about. It's like an effort to try and put all the characters in so you can represent all these different characters in. So you can actually do, you can subtract. So because of the spacing in this table above, they're always 32 apart between upper and lowercase. So, you know, we should be able to see that 65 is A and 97 is little case a, lowercase a. So you've got an offset. So you can just do the difference, and that will say 32, which we already did. So there's built-in functions in Julia. So you've got, again, confused, you can go uppercase. Uppercase of an abstract string will take all the characters, convert them to uppercase. You have this question. So how does Julia know this and transform A into the number 65 rather than displaying an error? It's to do, this is quite actually, that's actually a really, really deep question. It's to do with plus. So plus is defined on different types. This is actually a really deep question. It'll probably go to the end, towards the end of the course when you're getting up to Andy. If you add different types, so if you're going to do function my plus a b, if I go this guy is a type char and this guy is a type int, I can do something special. Whereas if a was of type int and b was a type int, then I can do something else. So Julia, I've jumped way too far ahead for you guys, but this is okay. It's a really important feature of the Julia language is this thing called multiple dispatch. So you can have the same function with different argument types and it will do a different thing. So it will do the appropriate thing at the appropriate time. This is one of these magical things about the Julia language is that it can do this. So I can have my plus for ints. I can just go, plus, I'm using the plus operator, so it will do the wrong thing. But you could imagine the character version. If you're using plus with a character and an int, it will know to return a character because that's what you want to do. I hope that answers your question. It's actually a good question and quite a deep question. It doesn't know, it has to be programmed. In the Julia language, someone's gone through and done all these overloads for all, all these different versions of plus for all these different types. It's the same as, where if we're adding big ints, it doesn't use the same algorithm as this. It's adding uint8s. Is this the same as overloading? Yeah, it's a type. So the magic word is, if you want to read up, it's multiple dispatch. So it's more like, what's the word? Parametric polymorphism. So it's like you can do different things in different situations. It's a really powerful feature of the Julia language. So it's like overloading, but yeah, more detailed. So the thing that makes Julia super clever is that it can work this stuff out and still be fast. It's like the only fast multiple dispatch language. It's like quite an achievement that it can work out for all these different types, what the right thing to do is and make it fast. You have multiple dispatch in other languages, but it doesn't tend to be quick. Sidetrack, that was a good question though. Okay, so if you wanted to make this function yourself that converts like uppercase, so, you can think of a thing you could do. So what's the obvious thing to do here for this function if we're going to make our own uppercase? Anyone want to be brave? Yeah, you just subtract off. So the problem is you'll have to do some checking. So you'll have to check that you're actually in the range of lowercase characters first, and then you can do this subtract off 32. Or add 32, whichever way around you're going to do uppercase or lowercase. So you do some bounds checking and do the thing. Otherwise, you'd probably leave it alone. So, for example, if you were going to do this, you want to leave the Z alone. Or if I did that, you want to leave that alone. So you only want to convert the lowercase characters to uppercase. So that's the case to check for. Good work, Mark. Okay. I think this is a cool example. So we'll go through this one. Then we're at the end of the section. So there's some funky syntax here. We'll have a go through. There's some bits to pull apart. Okay, so Julia has some libraries for doing things on the internet. So if you want to you can use these packages, HTTP and JSON. So we haven't talked about either of these things, I guess. So you should all know HTTP, internet web requests, but JSON is a data format, a particular data format, JavaScript object notation, I think is what it stands for. I'll have to check that before I go on, but so it's a data format. So what we're going to do is we're going to download, we're going to do a request at this website, a GET request. I'm going to download a big thing. This is at MIT. We're going to this web address. We're going to download a big text file of Shakespeare. Data is this HTTP messages response. So again, if you want to go type of data, it's a message. Cool. What do I do with a message? So I'm going to get inside the data. There's this thing called body. So another useful thing for you guys. I'll just teach you this one. You haven't talked about structs yet in Julia. But if you've got something more complicated, an object that's more complicated than arrays and strings and floats and ints, you might have this composite object that's a bit more complicated. So that's called a struct. This has some fields inside it, which will be either other structs or basic data types. If you want to know what's inside a thing, and you've just got one of these things because you're playing around in the REPL, you can do this function field names. It's super useful. That will let you go data.version 1.1. It'll say about this web request we just did. You don't need to know all this stuff. So that's like you get a 404 error or something you see on a web page. You've got some status thing. There's this thing in the body. So what this next bit of line is going to do is it's going to take the data in the body and turn it into a string. So remember, a string is an array of characters. This is actually going to be huge because it's Shakespeare. Blah, lots of stuff. It'll go forever. So we've got another function here that's useful for strings. So this is going to go for a while. That's why I didn't show it. And, oh, that works. Okay. So split. Again, if you're confused, split is a very useful thing. So it will split an array of substrings based on the occurrences of a delimiter S, DLM. If you don't give it, it'll just do it on the spaces. So the default thing here is it will take this big text file, and everywhere there's a space, it will cut it. So now we've got it will turn into words. Vector substring, blah. So we could look at the first element of this guy is this, is the 100th. So you could split on a different thing. So like if you wanted to split on a different character, you can put something in there. You can put a regular expression in there, which is something for later on, hopefully. You can on any character you want. So this is a really useful function for when you got a string and you want to cut it into 2 bits, say. So like if I've got a string saying this is, and I want to split this guy on the underscore. Actually, I'll change that so this is more obvious. Plus this plus. That's what split's for. So really useful for when you're doing string parsing. So Shakespeare words takes this data request. So we got some stuff off the internet. We turned into the body of this request into a big string, and then we split it into words. JSON words, this is another web request. Again, there's some stuff in here. So you should be able to see JSON words. Remember, there was this field body that seems to have the good stuff for the message. That's a bunch of uint8s. But Julia is clever enough when it's printing it to know that this thing is the JavaScript. So what we're going to do is we're going to, oh, sorry, JSON, not JavaScript. Terrible. So what we're going to do is we're going to parse this string into JSON. So this parse is a function of the JSON package that will turn this thing into JSON. So JSON is a nested data structure. Useful. So it's got these two bits. It's got num to show and words. So that's this parse JSON dictionary. So I'm not sure if dictionaries come up. That's another object that's really useful. So you can think of that as key value pairs. So it's like this guy is a label and then it's got some data underneath. So if I type in num to show, it gives me 5. And if I type in words. So basically, this is a special list of words that we're going to be interested in. So this, we're going to convert it to an array of strings from what it is. So we're going to get the words. So it was a vector of type any. We're going to make sure it's an array of strings. So just because it came out of this web request, it didn't know what it was. So it parsed it into a type any. This is another magical thing about Julia. It's like it can, if it gets confused about the type of something, it goes, oh, it's an any, but I don't really know what to do with any. So you have to, sometimes you have to convert it back to the string or give it a hint about how to decode some stuff. And we've got this. So num to show is 5. Okay. Now this expression is going to take a little bit of unpacking. So we've got a bit of a horrible one-liner. You can guess what it's doing just by running it. It's going through keywords and looking at this Shakespeare words, and it's counting how many times each of these keywords occurs in the original text document. I'll go through the syntax because I think this is a bit of an ugly one-liner. So hopefully I can, it's just a bunch of useful functions anyway. So remember Shakespeare words, let's go from the inside out. It's really this one is the magical one. So this is the function that's doing all the work. So this one, you guys should be familiar from last time, is a list comprehension. So if I just went X for X in keywords, that's really boring. It just makes an array out of the keywords. So you can imagine that this is just doing a list comprehension over keywords. So as long as we have one of these keywords, we can see what's going on. And we've got a tuple here where it's going X and keywords. So let's just say for a second that X equals the first one of keywords. Because remember, it's in a list comprehension, it's just going through one at a time. So what this function would do is it will make a tuple. So two values, they're in a bracket separated by a thing. So one of them is just the keyword itself, and then this function count. So count, okay. So Shakespeare words is this big list of words. So if you're confused about what a thing's doing, I'm going to say it a million times. Just put in question mark, type in count. Julia will give you an idea of what it's doing. So count the number of elements in iter in which the function f returns true. If f is omitted, count the number of true elements in iter. So this is a function that returns true. So if we're converting to lowercase, so these words might be mixed uppercase and lowercase as they're coming through. So it's like the first word in a sentence that will have a capitalization. So what we're going to do to make the comparison easier is we're going to convert everything to lowercase. So we've got this thing here is a function. So this, I'm going to talk about this in a minute, and you probably have seen it already, is an anonymous function. You would have seen it when I talked about map. I would have done something like map x goes to x squared 1 to 10. So this little bit is a function without a name. So what it would do is this, like if I'm given this argument, pass it through this function. So when we look at this count thing, what it would do is it will count the number of times. So this should work. Count the number of times this returns true for everything in this Shakespeare words collection. So one at a time we'll go through, pass it through this function. If the lowercase value of W is equal to the lowercase value of the keyword, then it will count it up. So that's the 300. Lots of syntax, but that is what this function does. So then you can take this array of tuples that you get out here and put it into a dictionary. So that's all that does. So that's a nasty one-liner. I don't think that's great, but you see a lot of syntax here. Is that clear? I've tried to go through that slowly, maybe too fast. There was a lot there. Everyone happy, or got one thumbs up, so that's good. I'll take it and go. Go through, confirm it for yourself. Okay, this other one might be really relevant to you. Okay, so sorted word count. So we've got a dictionary and we want to return it in sorted order. So you have this keyword last. You have a special named argument by, and this is actually a function. So last. If you're confused, you can go through and go last. So of some collection, give me the last element. So if I've got last 1 to 10, oh, sorry, not in the right collection. 10 gives me the last one. So what this guy is doing is that it will sort by the last element as it goes through one at a time in this dictionary. So we're going to collect word count. So collect is a 16 element vector of a pair of strings. So last will sort by the second one. So we've got 1. This has 2 elements. You get 1, 2. So when you give it this keyword by and you pass a function, it will sort by the last element. So basically it's going, I'm going to go through this thing. I'm going to get the last element, which is the count. And I'm going to sort in descending order. So that's reverse equals true. How was that? That's a lot of useful syntax for you guys. I think it's useful. So this as a general method is actually counting the frequencies of words in a text is actually a super useful thing. So we got these special keywords we got from, what was it? It was from this guy, these JSON words. There's these special keywords. If you wanted to make, these are all, they're probably a bit more, it's not, it's this anonymous function. So the question was, hi, I just want to ask about the W within the code. So W is an anonymous function. So you've got this special syntax. So it will take this value, pass it into this function. So it goes through, each time it goes through, it'll be one of these elements of this Shakespeare words will pass through this thing and get evaluated. So count takes a function. So you give it an anonymous function. And W is just basically taking one of these things, passing it through here. It evaluates this lowercase W equals lowercase x. So we'll come back. So have a play with it yourself. It'll make sense. The particular one to think through is like the map. If you have map, so I could call that W. I could have had something like x equals 3. I can go map x plus W squared. So that's sort of the same thing as what it's doing there. Hopefully that's clear. So anyway, back to what I was going. So these keywords, so a really useful thing to do in document classification is to just look at, say, the 1,000 most frequent words in English, and you can then use this pretty much this method where you go like, okay, I've got some document and I want to know what type of document it is. I can just count up the occurrence of certain words, and then I can turn the count into a frequency. So like if I looked at length Shakespeare words. So there's 900,000. That's a lot. So this is, they're actually, you know, any particular words fairly infrequent. So, you know, it's occurring 1,000, you know, 1/500th of the time king turns up. But you can imagine if you had like a bunch of keywords that are common in English, top 1,000 words, like or top 200, like Dr. Seuss, and then you count up the frequencies. It's actually a really reasonable way of classifying documents. All the early spam filters for emails are based on this. You make a feature that's the raw frequency of occurrence of words in a document, and you can tell. So this one's easy. Like you can go like, if it's Shakespeare, you're going to get thou art king, sir, England. You know, these sorts of words are going to turn up. But you know, if it's like spam email, you're going to get like Nigerian prince, enlargement pills. You know, all these sort of sketchy things coming up. Yeah, so you can actually, it's a really easy way to tell the type of document. And it's actually like, even though it seems super naive, it actually works really, really well. And all the early spam filters are based on this principle. So it's actually a super useful algorithm to think about it this way. So classify documents by the occurrence of keywords without any understanding of the structure of English. So, you know, other things you might look for would be like spelling mistakes or, you know, but even it's kind of funny how far you can get with a dumb algorithm. So it's just raw frequencies, not co-occurrence of words, anything complicated like that. It's just straight frequencies. You can classify documents. So you can have a play and see what you can do. So any questions from that section before I get started on section 2? I'll just wait for a second. All good? Okay. So that's basic intro to Julia. So hopefully that's all clear. You can start on Unit 2. Okay. I've tried to give a lot of hints leading up to this algorithmic thinking and algorithmic complexity. So algorithms is like, it's the thing. It's like, it's the bit I get most interested in as a software developer, is like the algorithmic side of programming is super fascinating and hard. And thinking about how you might transform a problem into this simple representation is, yeah, so that it will run on a computer. You say this understanding that how many operations, so when I was talking about addition in logic circuits, like what's the fewest number of logical operations I can do to do this calculation as quick as possible, is really cool. It's actually really fun, I think. It's hard though, so if you find it a little bit difficult to wrap your head around, it's fine. But as maths background people, this is where you're going to shine, I think. Problems tend to be discrete more than continuous, which is a little bit hard. So again, this prelude to complexity, I was talking about how you might do integration in multiple dimensions. That's like a big one. Like that's a mathsy type problem, like how you might actually go about doing that. How do you integrate a function in 400 dimensions? Because 400 factorial is a big, big number. Or 400 to the 400. So yeah, so algorithmic thinking. So got that basic start. Then we're also going to go, after we talk about algorithms and quantification of performance, also deal with starting to get some developer tools. So who's used Git before? I've got a rough survey. Has anyone used Git? I've got one no, one yes. So empirical frequencies looking like 50-50, no less, lots of no's. Okay, so Git is a version control tool. It's a little bit renowned for being a pain and confusing. So we'll start gentle, talk about that at the end of this section. So that'll be in a week or so anyway. But Git is really useful. You've probably heard of GitHub. So this is where code is hosted typically. Git is another beast altogether. So don't get these two confused. Git is a tool It's actually a distributed database. GitHub is a centralized database for code. Talk about IDEs. I use VS Code. We just started talking about text. Like, you can write Julia with a text editor. It's fine. I used to use Vim all the time. Anyone used Vim before? Yeah, a couple of people. I used to use Vim for Julia when I started all the time. I've moved over to VS Code because everyone I works with works in it, but Vim is it's actually powerful. You can make test.jl. You can just go inside. We can do a hello in this thing. So it's just a text editor. You just have to make a text file. So, and we can do this thing. So sorry if that wasn't clear what I just did. So I made a text file and made a text file called test.jl in Vim. I've just shown what's inside test.jl, and I've run it with Julia to do a hello world. So you just need a text editor. So VS Code's got some stuff that makes it a bit more friendly. So it'll give you syntax highlighting, and it'll tell you if you've got some errors. You can run a terminal from there. So it's just to make it a bit easier to do stuff. To write code, you just have to make text files. They're just characters that Julia knows how to interpret. And we're going to talk a little bit about basic Unix command lines. How's everyone's Nix flu? Some of you have used Unix-based command line stuff before, and some of you haven't, I take it. Okay, yeah, cool. It's a learning curve. It's really useful. Once you get in the habit, you'll see the power of doing things just in command line. It's much more useful. When you're actually working in software, it's normal to run things from the command line. So this terminal I've got here is a bash script. I'm sorry, a shell. So yeah, running things from here, running a series of basic commands that you can chain together is super powerful. And it's actually really good for understanding software design. The design of Unix, of having simple software Sorry, guys. Dropped out again. I have no idea why. Not great. Sorry, everyone. Disaster. Remote learning. What can you do? Where did I drop out? I think I might have been talking to myself for a little bit, but that's normal, so we'll see. Anyway, I'll get started. So yeah, I'm not sure, I noticed it sort of played up, but we're looking at sorting, thinking about algorithms, think about algorithmic complexity. Yeah, sorry, talking about Unix. So, okay, I think, yeah, it's something, Zoom's not playing nice. Okay, anyway, talking about Unix, blah, blah, blah. What we're going to talk about now is sorting. So the point I was trying to make, so I think I was talking to myself for a little bit, which is kind of embarrassing, but that's okay. Is that sorting itself is not an interesting application. The interesting application is thinking about algorithms. So don't get it's like sorting's not an exciting problem, but the thinking about algorithmic complexity is the interesting bit. So this one's straightforward. Won't worry so much about running in the REPL for this one for now. What we're going to do is we've got some data and we're going to sort the data based on something. So there's built-in sort. So the bit I wanted to highlight is that there's a bit of syntax here. Sort has an exclamation mark at the end. So this isn't an enforced bit of syntax. It's a convention. So when you're doing a program in Julia and you have a function that edits the input data, you put an exclamation mark here. So this sort, we'll go here. If you go question mark sort, there's two versions of sort. There's sort and sort with an exclamation mark. What sort will do without an exclamation mark, this is part of base Julia, is return an array that's sorted from the input array. So if we have A equals, sorry, we'll go this data one. If I go sort data, what this will do is it will return an array. So I've got X equals that. So data remains what it was before, and X is the sorted version of data. If, on the other hand, I call sort with an exclamation mark, this is a function that they've named and they've said that this guy modifies my input. This will actually change data itself. Hope that's clear. So remember, this isn't a convention. So if you're doing a function and it's like hi X, and you're going to go X equals X plus 2, return X. This will modify X. So you probably should, if you're going to do that, exclamation mark. And so if you're modifying, I can't remember the assignment question. So like doing assignment in place is a good idea for memory usage. You could do it, you could have an array, you allocate at the start and then you put everything into that array, or you could do it in place. I'm not sure based on the assignment question whether you should be doing sorting in place or not. I'd have to go and review the question, but generally doing it in place is a good idea for memory usage. Like if you don't care about keeping this thing, like if you're not going to use it somewhere else in your program, you may as well do it in place because you'll use a lot less memory. Yeah, okay, so the question is, how do you implement a sorting algorithm ourselves? So you can imagine, yeah. So you can imagine if you're going to sort an array, like you've got this data array. That's probably not the version of it we want. We want one where something's going to happen. So you can imagine like the dumbest algorithm in the world would be you find at each the minimum of this array at every iteration. So I'm going to scan through this array and I go, what's the smallest thing in this whole array? And it's like, oh, it's 1. I'm going to put 1 somewhere. Then I'm going to take 1 out of this array and I'm going to scan through it again and find the minimum thing. And then that's 12. Scan through again, 23, blah, 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 blah. So this thing I was saying about thinking about algorithmic complexity is like you don't want to be doing the same thing more than once. You know, like there's no point if if you've already gone through this array and you've gotten that one's the smallest thing, you actually know some stuff about you could have done some stuff on the way that was about the other elements of the array. So there's, a whole bunch of sorting algorithms. It's like a standard thing like to know about sorting in computer science. It's like if you go get a job at Google, they'll probably ask you a question about sorting. So it's good to know for that reason. The application, like I was saying, probably harping on that the application of sorting itself is not so interesting. It's more algorithmic thinking. This algorithm we've got here is called bubble sort. So bubble sort is a step up in naivety. So like the most naive would be that thing the most naive would be just like guessing randomly until you go, they're all in order, which would take forever. So this thing of like scanning through, finding the minimum, taking it out, scan through, find the minimum, take it out, that's terrible. So one step up in terribleness is bubble sort. So bubble sort is not a good sorting algorithm. It's actually a bad sorting algorithm and you shouldn't use it. There might be a version of the problem where it becomes useful, but bubble sort is terrible, but it's really good for starting to think about algorithmic complexity. So that's why we're introducing it here. We're not introducing it as a good algorithm for sorting. We're introducing it as a thing that, shows you how to think about algorithms. So what we're going to, I'll just go through it. Bubble sort. So this one, they're saying that we're going to do it in place. So we're going to keep this array and we're going to do some stuff to it in place. So get the length of this array, and we've got two loops. We're going to loop from I equals 1 to n minus 1, and we're going to go from j equals 1 to n minus I, sorry. So what we're going to do is we're going to look at each pair of elements in this array. And if one next to the other one, so it's really this inner loop is probably the one to think about in the first case. Don't worry about the outside loop first. You're going to do a scan through this array. And if the jth one is bigger than the j plus 1th one, so we're looking at this array. So we're going to go, is this guy bigger than this guy for 1 and 2? And like, yes. So if that's true, what we're going to do is we're going to take them and swap their places. That's the idea. So this, you can assign these two things at once. You could imagine having temporary variables. You're going to go like, I don't want to muss it up and do it out of order. So I'm going to make a temporary variable, pop this one into that, pop that one into that, and then write over them with the swapped versions. But you can just do them both at the same time. That's what this syntax is. So basically what you do is in this inner loop, we're going to go through. If the one on the left is bigger than the one on the right, we swap their places. And then we keep going through the array to the end, and then we stop, and then we swoop through it again in the big loop. There's actually, can anyone see something we can do to improve this almost straight away? Concurrency? There's something even easier. So I think about the data, like what's a property of A that might make this, might mean you can just go, it's done. Sorry, I'm probably not leading enough with my hint. I'll leave it for a bit. Anyone? Give you a chance to work it out. What you can actually do is you can check that if it's already sorted, then you only have to go through this array once. If this condition is never hit, so you can have a Boolean variable, you go like, if it's already sorted, I can stop. So this implementation here doesn't have that condition in there. You can just go, well, I can have a Boolean variable that's like, is sorted, and is sorted equals false. Oh, sorry, is true. And if this guy ever gets hit, then you set it to true. And then if you get to this, then you can break this loop if it's already sorted. So then you can just do one scan through of this array, and if it's done, it's done. And same on subsequent iterations of swooping through. If you can tell it's already sorted, there's no point sorting it again. So that's bubble sort. The name, oh, I'm scared of navigating around. The name comes from this idea that they sort of bubble through. So this is just from Wikipedia, the GIF of how bubble sort works as you do subsequent iterations. So you can see this thing starting with some data and iterating through where they're placed in this, as it represented as a permutation matrix. So you can see things falling into place. So they sort of bubble up to the top. That's where the name comes from, if that's not clear. So you can sort of see this percolation thing. So that's a way of doing sorting, not the best way of doing sorting. So what we're going to try and get you to think about, and this is like every time you write a bit of code where performance matters, and performance nearly always matters. So particularly if you're ever doing something in front of a person, people are really impatient and they won't like waiting. Or if you've got just a very complex algorithm. So that version I was saying of like, how do you do an integral in 1,000 dimensions? Quicker the better. Like it could be the difference between days and, hours or minutes, that's a huge difference. So just these performance tweaks, really, really important. So the key question is, how fast does it run? You can also ask, how much memory does it use? So this one, you should get an idea that running this guy, because it's in place, all we do inside this function is we make this variable n, and then we've got a bunch of iterators. This should be super efficient for memory. You're just working on this same array, but runtime, maybe not so much. Runtime, if it's already sorted, is good because you can just do this test and bail early. But yeah, that's the thing. So yeah, it's critical, not even just during, this says the design phase, but it's critical all the way through. Typically, particularly when using a language like Julia, you just want to bang it out as fast as you can and then make it fast later. But if your algorithm's bad from the start, different algorithm's going to be the winner. So we've got some examples of doing some timing. I thoroughly recommend benchmark tools for doing this stuff if you're doing it for real. This is just quick example stuff if you're copying it into your REPL. But if you're using benchmark tools, it's for doing proper timing in Julia. And if you're doing that, you will use something called B time, and it will give you a bit more information, and it will get you a better statistical sample of what the actual runtime is, because you can have this time macro lie to you. So this just times the function evaluation. So we've got some examples here. So a small data set, and comparing the inbuilt sort versus bubble sort for a small data set. They're both crazy fast, so don't worry about that. But if we go to a big number, so we're going to randomly generate 10 to the 4 integers and then sort them, their runtime difference is astonishingly different. There's a huge, huge difference in performance there. So what's going on there? So we're going to try and analyze the algorithm itself, and we're going to try and work out what's going on. So now this is this thing I was saying, like you can change the algorithm slightly. Change the software. You can do software engineering tricks to make this faster. So one thing you can do here is this macro inbounds. So what this will do, a macro again, it's a program that writes programs. So it's a useful function that's in base Julia that's given to you to avoid bounds checking. Now that's generally a stupid idea, but if you know you're never going to go outside your array, so basically that idea is like, I think I wrote one before. Let's see if it's here. Okay, I'll just reproduce this function. Okay. So bounds checking is when you index into an array, it will fail gracefully. There'll be errors, if you're trying to go like bigger than n. So what I've got here is a little function that just does a stupid sum where it's not doing bounds checking. So it will take the size of the array. So don't do that. Usually, if you're not dumb, you'd go like to the length of x, but if I'm going to pretend it's from the outside and I'll do this, at inbounds won't bother checking if this is actually inside the array, and it will start reading a random bit of memory somewhere else and interpret it as a number. So that will make it sometimes faster. So if you have an array if you have a problem where array access is slowing you down, which is usually due to memory and how memory is laid out, avoiding bounds checking can make it a little bit faster. So I just wrote this to show you, like, so x equals 1, 2, 3, 4, 5. If I go dumb sum to 5, 1 plus 2 plus 3 plus 4 plus 5. But if I go to 6, whoa, who knows what's going on there. So this is the danger of using this macro, but it'll get you a little bit of speed. So this is like a software engineering trick to make it faster. Sometimes it's really useful. If it's safe, it's safe. You may as well do it. If this came from a calculation where you're not guaranteed that it's going to be inside the array, it will give you a nasty bug with a fail where it won't. It'll be the worst type of bug. The best type of bug is it errors with a good message. The worst type of bug is that will error and not give you any information at all. So if I take my dumb sum function and I remove this inbounds thing, if I try and do that thing again, we've got error, you're trying to access a 5-element array at index 6. Like, why are you doing that? That's silly. Whereas if you put the inbounds macro in there, you won't get that error, and it will give you an answer, and the answer will be crazy. It'll be bonkers. So what you can see is that original bubble sort runs on 1,000, runs in this time. If you do the inbounds macro, you get like 15%. Like, no, yeah, that's not great. But it's nothing like the difference between these two. So this is for a smaller array as well. So we're only going on size 1,000. The difference between these two is orders of magnitude. So software engineering tricks is not the way to go fast. The way to go fast is to understand your algorithm. I think, sorry for all the failures tonight. I think that's a good place to stop. Do we have any questions? I'm happy to hang around and answer questions for a while.
I just got one question. I'm just considering, do you have any tips for balancing, optimizing processing speeds versus memory usage? Like essentially calculating information versus storing it? Or is it like pretty situational, really?
It's a problem to problem thing. Yeah, it's like you could.
Yeah, no, that's all right.
No, that's all right. I just got distracted by the chat. Yeah, it's definitely a problem to problem thing, and it's this idea of data structures in general. It's like, can you waste a bit of memory to make the compute easier? It's actually really problem to problem. Sometimes the memory thing is a bigger deal than the performance thing. So an example would be Google. Like if they're indexing the internet, that's a huge data set. So memory size trumps processing speed. So you burn a bit of processing because you can't deal with the size of the problem. Problems I deal with, because I'm not, it used to be a problem where I used to work. So, but, searching spatial acceleration structures and stuff, these acceleration structures of using a bit of memory, extra memory to make things fast is a good idea. So problem to problem, I can't give you a...
Yeah, no, that's cool. Fantastic. Cheers.
So I got a question from Aaron in the chat. In Python, I could initialize the array final equals final I, because it doesn't push to array. So the thing you want, Aaron, is push. So that's the usual way to do that stuff. So you could go A equals empty array. You can put a type on the array at the front, but you don't need to do that. It'll just be faster if you do. Let's just say it's this. And I can go for I equals 1 to 10, push a I. But, you know, comprehensions are usually better. Any other questions, guys?
So you said that bubble sort is inefficient. So what would you recommend instead?
We'll go through that. We'll go through that.
Okay.
If you look up sort, if you read ahead in the notes, the typical one that's used in most programming languages as a default these days is something called tim sort. But it's variations of either quick sort or merge sort. They're basically the ones. So we'll go through that though. We'll get there. I think there might be, yeah. We should go through that stuff. But they're the two. And tim sort's this hybrid one where it sort of does a bit of both. That's actually the name tim. So this is like the fast one is tim sort, but if you want to look up about them, merge sort and quick sort. But again, it depends on your problem. You can imagine applications where you'd want to do something that's worse. This is why understanding your problem domain becomes really important. So you could imagine a situation where this array you're going to sort, you don't know ahead of time. So imagine you're connected to the internet and there's users and they keep pushing new elements into this array. That's a very different problem than if you have the array already laid out in memory, and how you deal with one or the other are very different. So, you know, there's not a one answer. It depends on the problem. But for this typical problem of I have an array sitting in memory, I want to do it as quickly as possible, it's going to be some variant of merge sort or quick sort. And we'll tell you why. I'll tell you why probably tomorrow.
Because obviously a mutable data set's going to be faster to go through, right?
Yeah.
Like an immutable data set, like a dictionary.
Yeah. Actually, your lecturer for the last part, Andy, who works with me, is doing a bunch of work on making dictionaries really, really fast and doing those sorts of things really quickly. He just did a talk at JuliaCon, so the conference for Julia is on, and he just did a talk about his package dictionaries.jl that's trying to do things like that on those sort of data sets really quickly. So it's with enough software engineering effort, you can make things fast. Okay, any more? I think I'm going to try a different computer tomorrow night so I don't drop out on you guys. I'm very sorry about that. I hope the recording is okay. Thank you for your time. It's really late. Well done. Okay, see you later, everybody.
Thank you.